Hello.
Hello. Hello.
Sorry. Yeah, so I hope that my slides are visible. Um, Welcome to week 2 of these tutorial sessions. And yeah, I'm Mukta. I had taken this course 2 years back here at Sense, and I would be the TA for this course. Yeah. So I'll be handling the problem solving sessions. There is another TA for handling the weekly assignments. Okay. So yeah, in week 2, Prof has majorly covered, introduced everyone to what is photonic integrated circuits and what are the different components. And he has even given a brief history of how this technology has developed. So yeah, so today we would be talking about again introduction to photonic integrated circuits. We will be starting the topic of optical waveguides. So this might seem like going a bit ahead from the lectures, but bear with me because I did not find much material to make just on photonic integrated circuits. So let me know if you are facing any problems or you want me to clarify things. So yeah, we'll be doing only simple problems. So in details we'll do in the coming weeks. Yeah. Yeah, to introduce photonic integrated circuits, these are basically photonic components, but we are trying to miniaturize these components. So the idea is to get all these components on a chip like this. So here you can see that this is a PCB board, just like electronic circuit PCB board. And then on top we have mounted a photonic integrated circuit chip. So this is the chip, and then there is some flip chip bonding here. So these are the fiber arrays. So all these fibers are so light is coming through these fibers, and then it is getting coupled to the chip. So there might be some grating couplers here, and then they have aligned it perfectly so that the light gets coupled, and then there can be any number of devices here, waveguides, splitters, or whatever the application demands. And then these things that you see here, these are the wire bonds. So for photonic circuits also, we need some electro-optic modulation, or even other type of like acousto-optic modulation also requires some electrical signals, right? So these can be then connected to DC power sources or some RF sources based on the application. And so you see these gold things, those are the metal pads. So yeah, so that's how our photonic chip will look like. So for making such a chip, what do we require? So we require uh, an analog of an optical fiber. So optical fiber basically guides light, right? So similarly we can have planar waveguides on the chip. So this is an example of a planar waveguide. So it has a silicon core, so and a SiO2 cladding. So you might be aware that optical fibers are made of uh, SiO2, right? But then the SiO2 of the core is slightly doped. Silica in the core is slightly doped compared to the one in the cladding. So because of that, the refractive index of the core will be slightly higher than the cladding. In case of on-chip waveguides, we need even more higher confinement, right? Because we are dealing with even smaller dimensions. You can see the scale here. So because of that, we choose silicon as the guiding material. It has a higher refractive index, somewhere around. So it will depend on the wavelength, but around this number. And then the SiO2 cladding will have. Anyone trying to join? Okay, no, sorry. And the cladding will have a refractive index around, I think, 1.5 ish. So the contrast will be higher because we need a stronger confinement. And yeah, so that is the waveguide. So once we are able to guide light on a chip, we also need the light to be coupled to a chip. So there are many ways we can do it. So in bulk optics we usually use a laser, right? So in integrated optics we can integrate such lasers on chip. So there are many different methods of doing it. One is hybrid silicon laser. So in this case there will be a waveguide, right? So on top of the waveguide uh, they will bond a indium phosphide based laser or some lasing material. So they will they'll fabricate this material on a separate die or a separate wafer in a separate process, and then they'll do a bonding onto the waveguide. Yeah. So, so this is more probably the lowest cost. Like potentially, if this technology develops, it is in like people are just starting to do this. So, if this develops pretty fast, then we will be able to bond multiple lasers on the same chip at the same time, and that's why it is potentially the lowest cost method. Another option is to have an off-chip laser. So just like what was shown here, right? So there was some laser here, and then the fibers from that light source were laser or any other light source were brought to the chip, right? So then that is also possible, but there we need the optical fibers. So yeah, requires fibers, and so here they have given a proper alignment groove, and then they have shown how they are edge coupling into the waveguide. So this is the waveguide, this is the fiber, and they are coupling edge to edge. So the open edge of the waveguide, light from the fiber edge is getting coupled to the waveguide edge. So here it was from top, right? Here it is from the edge. Similarly, we can do edge coupling by attaching the laser on top of the chip. So this is also possible. Yeah. Okay. So that was about how to get light and how to guide light. Then what other functionalities we might need? Say that will depend on the application, but simple ones can be like a modulator. So say you want to do some optical communication task, and you have a signal or a sine wave or some kind of signal, and you want to say it's in the RF domain, in like an electrical signal, and then you want to put it on in the optical domain. So then you will use something like an intensity modulator. So this is the RF probe here. So the RF input will go in here, and then there will be some context for giving a DC bias also, and then we will send laser light into one fiber, and the output light will be modulated light. So this is how it is done in fiber optics or in bulk optics, but when we try to do it in on-chip photonics, so we need on-chip devices. So inside this modulator we basically have a MZI or Mach Zehnder interferometer. So it will be like one, so light will get split into two arms inside, and then there will be a phase shifter here that will be tuned by this RF. So the interference that is happening at this end, so there will be phase shift due to this phase shifter here, and this phase shift will get translated into an intensity change at the output. So that is what is happening inside an intensity modulator. Same thing we can do on a on-chip modulator. So the light can be coupled, say, from this arm. This is a grating coupler. I can have a fiber coupling light into this arm. So this is a waveguide, and then this is a splitter. So we'll learn how this actually splits. This is called a directional coupler. So this can be used to split light into two arms. And then we can have a phase shifter here. It's not shown here, but we can have a phase shifter here that will change the phase, and then at the output we will see a modulation. So we can take it here also, here also. Is that okay?
Ma'am,
Yes.
ma'am,
Yes,
in
yes.
the board, so both arms we are sending the input, right?
Uh, so the device picture that I found out has a two input device, but we can even have a single input device. So here, like if we just want a device like this, uh,
Hmm.
then we can send light only in one arm. So this is a 50-50 splitter.
Okay, okay.
If we send light only in one arm, it will split into 50-50. If we send in both arms, then based on the phase shift between the light in this arm and light in this arm, the coupling will change. Right. So it's actually a
Okay.
directional coupler, but if we just send light into one of the arm, it acts as a 50-50 splitter. So it will get split
Just
into
like the
two arms.
beam splitter that we use.
Exactly, just like a beam splitter, just an integrated optic version.
Okay.
Yeah, so these are basically two waveguides. So when the waveguides come close to each other because of evanescent coupling, some part of light intensity will travel to the other waveguide. Okay,
Okay, ma'am.
thank you. Sorry. Yeah, so that's like a modulator. Uh, Next, obviously, we'll also need a detector. So bulk optics, there are many options for a detector. You can use avalanche photodetector or any kind of PIN diode also works. So like a lot of commercially available detectors are there. You'll send light through a fiber and then it will get converted into an electrical signal. So that is the functioning of a photodetector. Similarly, we can do a similar thing even in on chip. So we need to smartly choose the material. So based on the wavelength of the input light, so you ignore this ring here, but this is the waveguide. Light is coming through the waveguide, and this MOSE2 film that is deposited on top of the waveguide, this is sensitive uh, to the incoming light. So based on the light intensity, uh, it will generate a current across this. So so these are the gold pads, and this is a wire, and yeah. So if it sees a photon coming in, there will be some transition, and a carrier will be generated, and that will translate into a current, and we can detect that current. So yeah, so it is possible to, yeah, it is possible to get an on-chip photodetector as well. So what do you guys think might be the advantages of using photonic integrated circuits?
Communication speed will be faster
For optical communications, why will it be faster?
Because it will be communicated with the speed of light.
Oh, you are comparing it against electronics, right? Yeah, that is true. uh, Obviously, so it's not because so yeah, you saw right in the earlier slide. So we usually have a signal in the electrical form, so say an RF sine wave, and that I will send to a phase shifter. So based on my frequency of the RF wave, I can tune my optical frequency, right? So then don't you think it will still be limited by this the speed of the electronic signal that I can send to the optical signal? Because at the end of the day, we have to write on, so we have to encode the information in optics for communication and decode it. And this encoding and decoding part we are always doing in electronics, right? So, how do you think it will help in getting faster communication? Yeah, so I can give you a hint. So, hello, are you trying to speak?
yes ma'am.
Oh, okay. Yeah. So one hint can, if you look at the bandwidth of operation that we can do. So um, so we can actually do something known as wavelength division multiplexing. So to simply understand this concept, we basically put information in different wavelengths of light. Just like how we receive radio signal at different frequencies, right? Similarly, we can have a WDM setup, wavelength division multiplexing setup, in which we have multiple laser frequencies that are input. Now, each of these frequencies, I can actually encode different data on it. So at a time I am sending more data compared to the uh, available bandwidth for electronic applications. So this is also done in RF, but the point is the number of wavelengths available for,
Bandwidth is less.
yeah, bandwidth is less, exactly. Yeah, so that's
Okay,
why
ma'am.
we can get faster communication. So any other point? So why would it be better than using fiber optics, bulk optics for us?
Bulk optics will have larger attenuation.
True. So if we have longer fibers, there will be since these waveguides are like you can imagine in some 1 centimeter across 1 centimeter chip, the length, the loss will increase with length, right? So as you said, right? So bulk optics will have more attenuation, and we will need higher laser powers to accomplish the same task compared to the. Uh, so I can just say low attenuation or low loss, right? Right. So yeah. Yeah, miniaturization obviously. Also, it will be low cost because so in when we are fabricating PICs, we can make like a lot of components at the same time, and we can have a lot of components on the same chip. And yeah, so that will reduce the cost of instead of buying each and every component and making more complicated circuits. Um, in the same fab run, I can potentially fabricate multiple devices or multiple photonic integrated circuits also. So it will be probably potentially low cost. Yeah, we can make larger circuits, and as you said, low power consumption. So I was actually comparing with fiber optics, so I wrote these 4 points. But if you compare it with electronics for certain applications like communication, obviously it's also faster than RF. Yeah. Yes, so the first basic, most basic element of all photonic integrated circuits is an optical waveguide. So optical waveguide is not like exclusively just for PICs. Even a fiber, we can think of it as an optical waveguide. So it is basically anything that guides and confines light waves. Right. So so what is the basic working principle? It is total internal reflection. So whenever light is incident from a higher index medium to a lower index medium, it above a certain critical angle, it will be totally internally reflected. So there won't be any refraction part. It will be all the light intensity will be internally reflected. So this is the basic ray optic picture of how a waveguide works. So there are two conditions. One is core index should be higher than clad index, as we know, and then there the angle at which the light is being incident at the interfaces, it should be greater than this critical angle. And this critical angle we can derive it from the Snell's law, and I guess most of like we all know this, right? So yeah, so just as an example, we can try finding the critical angle for a typical optical fiber. So in an optical fiber, we have silica. So core index will be 1.465 and a cladding index will be 1.45. These values they have given. calculate the critical angle for total internal reflection at the interface between core and cladding. So yeah, you can calculate this. So if you just do an arc of this, arc sine of this, you will get somewhere around 80 degrees, 81.8 degrees. So you see, so every angle that is incident that is greater than this 81.8 degrees, uh, based on this working principle, that should be confined in the waveguide. Okay. So another parameter when it comes to optical waveguides is the numerical aperture of the waveguide. So what is numerical aperture? Numerical aperture basically quantifies how much light will be um, so what so the total uh, um, angle. So okay, so you can say it is the light gathering ability of the waveguide. So it depends on this theta a max. So the total half angle at which the light can be incident on the waveguide, and it will be still totally internally reflected in the waveguide. So if it is above this angle, what will happen is we will see that it gets inside the waveguide, but then since this angle is lesser than the critical angle, so instead of being totally internally reflected, it will just be refracted onto the other side. So yeah, so the numerical aperture quantifies how much is this gathering capacity of the waveguide. So as you can expect, it depends on the core and the cladding refractive index. Yeah, so this is the formula. uh, so it is defined as the sine of half acceptance angle. So this is the full acceptance angle, and yeah, with the respect to the normal, it will be half acceptance angle. Yeah, so a simple problem based on that. So yeah, so they're defining refractive index contrast as this. So this is the relative refractive index difference. So this is the refractive index of the core, which will be higher than the cladding, and then they squaring it and taking the difference upon 2 times n core. So that is the refractive index contrast. So we have to state whether it is true or false. A large refractive index contrast results in a large acceptance angle and large numerical aperture. So if I have a strong refractive index contrast, I can confine more light. So even at steeper angles, I can confine the light. Is it true or false? So yes, Jayesh.
Yes, ma'am.
Yeah, I thought you said
It is
something
true.
like true, huh?
It is true.
Yes. So you're right. Yeah. So we can simply see it from the definition of numerical aperture itself, that the contrast is Na square by 2 times n core. So based on this, if I just write Na as square, so it's proportional to square root of the refractive index contrast. So higher the contrast, higher will be my numerical aperture. And similarly, since numerical aperture is nothing but sine theta I, so then that will mean that I can have larger theta I. So yeah, the next problem. Find the refractive index contrast, numerical aperture and maximum half acceptance angle for a waveguide with core index equal to 1.465 and cladding index equal to 1.45. So this is typical of a optical fiber. Let us just do it to revise the formulas. So yeah, so the refractive index contrast is defined as so yeah, that's just by substituting in these equations, you should be able to get all the three values. In case you get this in your assignment problems, you can keep these equations handy. So I'll just write the final values. So we can see, right, for a typical optical fiber, the refractive index contrast is basically 1%, right? Now we can contrast this with, next we'll find it for a waveguide. We can see how this contrast is different for a waveguide. So yeah, so till now we were saying that any angle greater than the critical angle, if we look at the ray optic picture, it should bounce back and come as a totally internally reflected light, and then this process should continue down the waveguide. Yes, but so when we go towards smaller dimensions, we see that this ray optic picture is no more valid, and we need to consider this light as a wave. So if I consider it as a wave, and these are my wave friends. Okay, wait. So I have drawn here the wave fronts for this light beam and this light beam. So what do you think will happen if their phases do not overlap in the places where the wavefronts are overlapping? So basically, so when we're thinking about waves, if two waves overlap with each other and say they are shifted in phase, then we observe something known as interference. So at some portions, just like that two slit experiment that we were taught, at some portions the wavefronts will overlap and we'll get a constructive interference, and some other portions will get destructive interference. Right, so it will be just a sum, the electric field profiles will just be a sum of both the profiles. And so say if this is my first wave and this is my second wave, then the net will be destructive interference. So we won't see any light. It will be dark. Right. So basically from this phenomena we come at something known as phase matching condition. So whenever the difference in phase, so the phase difference between two wavefronts that are overlapping, whenever it is a multiple of 2 pi, then it will be a constructive interference. So if the angle of incidence is such that the waves interfere destructively, the waves cancel one another and do not travel further. If the angle corresponds to constructive interference, the results in, whether it will be constructive or destructive interference depends on these path lengths, the phase shifts at the interfaces. Yeah, so these path lengths are determined primarily by the angle of incidence, right? So how at what angle the light came inside the fiber will determine. So till now we were saying that uh, any angle greater than theta c will suffice. However, now there is an additional condition: the particular angles at which the light is traveling inside the waveguide. So only particular angles will be able to travel. So depending on this m, and and these are called optical waveguide modes. So corresponding to the different thetas that we have, so all these thetas will be greater than critical angle. Sorry, but there will be certain distinct number of thetas. So yeah. So yeah, similar thing we can see here. So there can be a mode for corresponding to m equal to 0, corresponding to m equal to 1, 2, 3, like that. Yeah. So the waveguides that allow only the fundamental mode, that is the mode corresponding to m equal to 0, that is delta phi equal to 0. That particular wave is that particular waveguide is called single mode waveguide. If more modes propagate in the waveguide is called multimode. So for a given wavelength, the indexes of refraction and core cladding, there will be a maximum radius for the core of the fiber that allows optical waveguide to be a single mode. So what does this mean is, so, uh, so we saw previously, right? So if I want only a single mode to propagate in my waveguide, I have to uh, reduce the width of my waveguide. So for smaller waveguides, uh, the other modes will be uh, so that is how we make a single mode waveguide, by reducing the dimensions of the waveguide. So let's see how we know if my waveguide is a single mode waveguide or a multi-mode waveguide. Okay, so to determine that, we define a parameter called V parameter. So the exact derivation of how this parameter is allowing us to determine whether it's single mode or multimode, we will be covering in future classes. However, for now, just we need to understand what it depends on. So uh, what the number of modes traveling in a waveguide depend on. So this V number can tell me whether a fiber is single mode or multimode. It can be calculated using this equation. So you see, this is again the numerical aperture coming in here, and this k here is nothing but my wave number, that is 2 pi over lambda. So for the case of optical fibers, so for any for fiber of the form of a cylindrical geometry with a step index core, so a core and a cladding, it has to be step index. Then if V is less than 2.405, the fiber is single mode. So how we came up with this number, we will learn in future classes. But for now, we need to understand that. So the number of modes that are trapped inside this waveguide will primarily depend on the refractive index contrast and the wavelength of light, and also obviously the geometry. So this number will be different for, say, a waveguide, a rib waveguide, say. or for a planar waveguide. So for on-chip waveguides, this number will be different. For fibers, it will be different. For any other geometry, it will be different. So yeah, based on this formula, we can do certain problems. Determine whether an optical fiber with core radius equal to 9 micrometer and cladding index of so much and core index of, oh, they both are same. So we can take this core and cladding from previous questions. 1.465 and 1.45. Sorry. And the operating wavelength of 1550 nanometer. We have to tell if it is single mode or not. No, sorry. They are different actually. It is 1.445 and 1.455. So it's very slight difference, but they are different. So yeah, we can determine the V number. So for determining V number, first we need to find out what is K. So K is nothing but 2 pi by 1550 nanometer. And then we can determine V. We'll write everything in micrometers. Hello. So this A I forgot to tell. A is nothing but the fiber core radius. They have given it to be 9 micrometers.
It's multi-mode, ma'am.
It's coming out multimode. Okay. Yeah. So you can just substitute and check. Thanks. Thank you, Jayesh. Okay. Yeah, so still now we were doing all the problems based on fibers. Now let us move on to planar waveguides. So planar waveguides are one of the type of waveguides that we can make on a on-chip platform. So, yeah. So in this picture we are seeing a slab waveguide. So for a slab waveguide, there will be a slab of high refractive index material at the center, and then there will be cladding and substrate. So both these will have refractive indices smaller than the core. So typically this won't extend till infinity. We will have a very wide, so this width will be very wide compared to the thickness. So then we call it a slab waveguide, or we can say with a very thin core and a wider width. Okay, so this can be fabricated on a silicon chip. Say we can have oxide SiO2 at both the core and cladding, and we can have silicon or any higher index material like silicon nitride at the center. Okay. So the only parameter that describes such slab waveguides is the this 2A that is given here. So we have just used 2A to refer to the, because we said A was the radius in the case of fibers. So this is like the diameter, right? So that's why they have just put 2A. So similar to the fibers, now we can do the same thing for planar waveguide also. Determine whether a slab waveguide with thickness equal to 6 micrometers, cladding index of 1.445 and core index of so much. Okay, so these values are again for silica only, operating at the wavelength of 1310 nanometer is single mode. Calculate also the refractive index contrast between core and cladding. And for the case of single mode slab waveguides, the V has to be less than pi by 2 for the slab waveguide to be a single mode. The same thing that you did for the previous question, we have to do it here again. So just be careful here. A is not 6 micrometer but 3 micrometer. So we have to, 6 is 2A. So we have to take only A. So A will be 3 micrometer. V is 2 pi over lambda times A times my refractive index difference. And then we have to remember to take the square root also. So what is the value that you are getting? Is it lesser than pi by 2 or greater than pi by 2?
It's lesser, ma'am. So it's single mode.
Yeah. Yeah, thanks. So can you tell me the value? I can write it.
1.548.
Thank you so much. Yeah, so it is less than pi by 2. Uh, pi by 2 I think will be something 1.6, right? Yeah. So yeah,
Yeah, 1.57.
yeah, thanks. So then what does it mean? It is single mode, like you said. Also, they've asked us to calculate refractive index contrast. I am sure you can do it if like just this divided by 2 times n core. Okay. So yeah, so that was about planar waveguides. So typically, like more commonly, we use this wire waveguide or rib waveguide like geometries. So in wire waveguide, we will etch the core material completely till the substrate is reached. So the only region where light can be guided is this portion. Naturally, it provides higher confinement compared to rib waveguides. In rib waveguides, we will etch it. It will be a shallow edge. So the higher index material will be here also. However, because of the width and height difference between this region and this region, the effective refractive index here will be higher compared to here. So this portion will also act as a um, lower index material. So the mode profile inside this will look something like this. So yeah, here so contrast will be lesser compared to here. So this will be less like the confinement won't be as much as in this case. However, this is also preferred in some cases where we want to reduce the loss due to sidewall roughness. So when we are etching it through and through, because of the roughness in the etching process, the losses might increase. So they sometimes go for shallow edge waveguides. So there is another type of waveguides which are like very interesting. They are slot waveguides. So instead of the light being confined in the high index material in this case, it gets confined in the gap between the two materials. So the effective refractive index turns out to be such that it is the light gets confined here. So all these things we can actually do the solve the electromagnetic wave equations and get these waveguide mode solutions. And yeah, some of these cases we will be doing in the coming classes. So another thing, this thickness, right? Thickness of the high index material, it it is something that we cannot change at different places on the same photonic integrated circuit. So for one circuit, since we will first have a substrate, we will deposit one material on the substrate, another material on the substrate, so the stack will be defined before only. So this height we cannot change much. So the only thing that we can change is the width. So we can only vary waveguide width according to the application. And so if we increase the waveguide width more, it might change from a single mode fiber to a single mode waveguide to a multi-mode waveguide. Okay. So yeah, calculate the refractive index contrast of silicon, refractive index 3.5 and silica 1.45. Compare this with typical contrast for silica or doped silica. Silica and doped silica. So this we had already calculated before. Uh, it was around 1%. So if we just calculate the refractive index contrast in the case of this one, for silicon and oxide. The core is 3.5, so below we will write 2 into 3.5 square. Yeah, so I had done this before, so it comes out to be 0.41, that is 41%. So you see the difference, right? Just because the waveguide dimensions are smaller, we are going to such high refractive index contrast. So the confinement is also stronger. So waveguides tend to be multimode when the refractive index difference between core and cladding is large or small. Multimode.
Large.
Yes.
But it is more large.
Large, huh?
Large.
Large,
Yes.
large.
Yeah. Yeah. So higher refractive index contrast will mean that the V that we calculated will
Number.
also be. Yeah. So the waveguides tend to be multimode when the dimensions of the core are. If I just write the V formula, I think it will be very easy.
It's large and
Uh, yes. Yeah. So for single mode, we have to go towards smaller waveguides, and for uh, or we can have a smaller refractive index contrast. Yeah, so from this we can conclude that if my refractive index difference is higher, so then I can go towards smaller and smaller waveguides for getting single mode operation. Yeah, anything else that I wanted to? No, I think. Yeah, so that's it. Thank you for attending today's class. Yeah, you can ask if you have any like doubts in the assignment questions, but I cannot discuss them right now, like the solutions right now, because the deadline has not passed yet. But in case you have any doubts in first week or second week. Yes, Priyadarshini, I could.
Ma'am,
Oh, sorry. Yeah.
hello, ma'am.
Yes, Jesh. Yeah.
Ma'am, in one of the questions in the first assignment, they asked about the direction of the wave vector, but then the answer available was like the allowed answer was having only a number kind of.
I remember that. Like even in last class, I discussed that it was a very ambiguous question. So this one, right? What is the
Yeah,
direction of the k vector? So
yeah,
what I
yeah,
will suggest is for now, uh, so the direction of the k vector you can write it as something I cap plus something j cap, right? So sorry, the
yes,
k vector I can write it as some number here and some number here. So it turns out
yeah,
that this number will be same because it is
hmm.
45-degree. So you can write it as
Yeah.
that number times I cap plus j cap.
But if
Then you just write this number
I'm
for the
just to
time
write
being.
I and J.
No, don't write INJ. Just write this number for the time being. I will check with professor uh, about the direction. So there will be some correction in that question. Don't worry. But for now, you just write this number down.
Okay, ma'am.
So actually, the other TA is supposed to look into this. She will be, if you just post on the doubts section, right? I think she will look into it.
Okay, ma'am. Sure.
Okay. Any other problems? Week 2 seems straightforward. Oh, are these things discussed in class? Transverse electric, transverse magnetic, like mode polarizations and all.
Yes, it was discussed in the week 2 lectures.
Okay, then fine. Yeah, okay.
Briefly, sir discussed it, not completely.
That's what. Like I was thinking that this will come in when they discuss waveguides, right? Like how to get different mode solutions and all. Okay, if he has briefly talked about it, you can do this also. Okay, so
I
thank you.
have only one query. It's
Yeah.
not from the assignment.
Okay.
Uh, whether these doubt sessions or problem solving sessions recordings will be available?
Yes. So if you just go here, problem solving recording, you can click here. You can see the screen, right? And then
Yeah.
go
Yes.
here. Yeah, so here is the YouTube link to view the presentation or the class, and this is the folder for presentations. Recordings, they are not shared, but you can see the YouTube. Like that is fine, right?
Oh yeah.
Okay,
Thank you.
okay, thank you.
Thank you, ma'am.
Thank you. Thank you. So I'll close the session. If you have anything that you want me to discuss in the next class, you can mail me. Uh, I'll just put my email address here. Yeah. Feel free to mail me so then I can prepare those topics and come for the next class. Okay, thank you.